Okay, a piecewise function. And we're going to investigate the continuity or discontinuity of this thingamabob in 3 steps. 3 steps, yeah, 3 steps. First of all, I will notice that my function breaks at x equals 1, and then it breaks again at x equals 4. Well, I mean the definition changes. So I'll write that down. 1 and 4. So the first thing I'll do is I will look at x equals 1. Then I'll look at x equals 4, see what's happening there. And thirdly, I will look at the spaces in between 1 and 4, or less than 1 or bigger than 4. So x not equal to 1 or 4. And then finally, I'll do a sketch. Okay, x equals 1, what's happening? Is my function continuous there? So to be continuous, you need the function to be, first of all, defined there, right? At x equals 1, it is defined. You just use this definition. There's no problem there. So I just need to check that the limit as x goes to 1 from the left equals the limit as x goes to 1 from the right. Okay, so this will ensure that the overall limit exists. And then I can check that it equals the actual value of the function, which will be 2 to the 1. So let's calculate these two limits. So for the left-hand side, I have 1 minus, so I'm less than 1. So here I am. First definition, I use this definition, 2 to the x. So limit x goes to 1 minus 2 to the x. I suppose I should put a question mark here. I'm trying to evaluate whether, this is a question mark here. I'm trying to evaluate whether these two things are the same. Still a question mark here. So for 1 plus, I am in my middle zone, my middle region. I use this definition. 1 over x minus 3. So I get 2 to the 1 here. And on the right-hand side, I get 1 over 1 minus 3. And these are obviously not the same. So my conclusion is that limit doesn't even exist at x equals 1. Therefore, discontinuous. Okay, x equals 4. What's happening there? That's the wrong green. I don't want green, I want blue. Am I using green? Oh, whatever. Green, why not? X is equal to 4. What's happening? Limit. X goes to 4 from the left. Let's see if that equals the limit from the other way. So when I'm coming from the left, I use 1 over x minus 3. And when I'm coming, x goes to 4 plus. I use the last definition, which is root x minus 1. And lo and behold, I get the same thing, don't I? Okay, in both cases I get 1. So, big check mark. So my two limits agree. So the overall limit exists at x equals 4, and it equals the value of the function. So I can write that down. Limit x goes to 4 of f of x. That actually exists, and it equals f of 4, and in both cases they're equal to 1. So therefore, continuous at x equals 4. Okay, now what's happening away from 1 and 4? What is happening? What is happening? So let's focus here. So for x less than or equal to 1, we have an exponential function, which is continuous. You see there's no problems here. You can, 2 to the power of any number, you can calculate that. In the middle, this guy has a problem, right? There is the possibility of a division by 0. And that occurs at x equals 3. So I'll write discontinuous at x equals 3, a division by 0. Now finally, for x bigger than 4, are there any problems? Well, root x would have a problem for negative values of x, but that is none of my concern here because this definition is only being used when x is bigger than 4. Okay, so there's no problems there. Okay, so I looked at what's happening away from x equals 1 and 4, and I only found one discontinuity. So I'll make note of that. Discontinuous at x equals 3. Okay, so what are the discontinuities? Well, we found this one, and we found the discontinuity at x equals 1. So those are our only 2 discontinuities. Now, we're asked further to see at x equals 1 and x equals 3, we're asked further to see whether we have continuity from the left or from the right. So let's do that. So looking again at the definition of the function, at x equals 1, it appears as though when I approach from the left, I have continuity. And at x equals 4, well, we're going to have to see. X equals 4 is not the problem. X equals 3 at the other discontinuity. At x equals 3, what's happening there? Well, that's a division by 0, so I suspect we're going to have nothing happening there. Okay, so let's summarize some of this. So we have discontinuities. At x equals 1. and x equals 3. Now at x equals 1, we have limits as x goes to 1 from the left of f of x. That will indeed equal actually f of 1. Because here we use the 2 to the x definition, and here we have just 2 to the 1. So we get 2 to the 1 is equal to 2 to the 1. Yes. So we say continuous from the left at x equals 1. Okay, but if you look at the limit the other way, if you look at limit x goes to 1 plus of f of x, okay, is that going to equal f of 1? Well, when you do this limit, you use the other definition, which is x minus 3. And here you get 1 over 1 minus 3, not equal to 2 to the 1. So this is not continuous from the right. At x equals 1. Now what about x equals 3? At x equals 3, f of 3 doesn't even exist. So f equals 3 dne. So, so this cannot be continuous there from the left or the right. So f is not continuous from left or right at x equals 3. Okay, when you're doing continuity from the left or from the right, you need like this limit. X goes to say 3 minus. Okay, you need that to equal f of 3. Now, if this thing I'm circling here doesn't even exist, then you are in some trouble, aren't you? Okay, this equation doesn't even make sense. Okay, so the function is not continuous from the left or the right at x equals 3. Okay, let's do a sketch now. Now, let's see if I can grab this function and bring it down. Pin. Why did I pin that? Bring it down with me. Come on down. Come on down, buddy. Come on down. Oh, there it is. Hopefully that's visible. All right, we want to sketch this. So what does 2 to the x look like? Well, 2 to the x looks like, it's an exponential function. Oops. It's exploding up to infinity, but then it comes down, approaches the x-axis. Okay, the function 1 over x, the most basic function 1 over x looks like this. It's called a hyperbola. Goes like that, goes like that. Okay, it's approaching the x and y axes, but never touching. Now, if I want to graph 1 over x minus 3, you have to move, you take this guy, and this minus 3 down here is going to shift my function to the right by 3. So I'd have the same shape as I do here, but now it's been moved to the right 3 units. So I can just go put 3 on my graph here, draw a dotted vertical line. It's kind of like the new y-axis. And then you have the same shape as before. Like that. Oops, I screwed that up, didn't I? It's in the wrong quadrant. So I should be doing it over here. Okay, like that, and then like that. Okay, so again, I took the basic hyperbola and I moved it over to the right by 3. Now the square root function. The square root function, what do we do here? The square root function is actually a parabola, or part of a parabola. You know the basic parabola, this would be x squared. We'll go like this, right? Now what you do is you turn that on its side. So you go like this. And then you're going to have to delete the bottom bit because root x is always positive. And now if I want to do root x minus 1, then I need to take this guy and move it down by 1. So I take my root function here and I move it down by 1. So what do you say? Put a 1 there. It's going to go through 0 here. If you want to get specific, you can notice that root 4 minus 1 is going to be 1. So when x is 4, y is 1. So it's going to go through this point, and this point. Okay, so basically again you have just the basic square root function. I do actually hit this point here. I do hit this point here, and I do hit this point here. Okay, now I'm going to put these all together to form our piecewise function. Let's make it nice and big here. So breaking out 1 and 4. Let's go breaking at 4, 4. Ooh la la. 2. Minus 2. There's my 1. All right, so for x is less than or equal to 1, so that means over here, I want to follow the 2 to the x definition. Or I just want to draw 2 to the x until I get to x equals 1. So if I put 2 here, if I have x equals 1, I'm going to have y is equal to 2 because I'm using the 2 to the x function, and I plug in 1 and I get 2. So I'm actually going to go through this point here. I'm going to achieve this point here, and then it's just, as I did above, it's just this exponential. So something like that. Continuing to the left forever. Okay, and that's the definition I use from minus infinity all the way till x equals 1. Okay, between 1 and 4, I'm doing the hyperbola. The hyperbola was trickier. What was that? What did that look like? That was this guy up here. Right, I'm using this definition. But just from 1 until 4. So I just want to take this chunk of it and move that down there. You don't have to be super accurate here. We are sketching after all. Don't be afraid to just plug in values. So if I plug in 1, I get -1/2. Roughly here. It's going to be an open ball. This is not a 0 here. This is an open ball. And this is a closed ball. And then I have my vertical asymptote here. So my function is going like this. Oops, no, I screwed this up. Because remember the hyperbola is going like that. Oops, like that, right? So I want to take this arm and put it right there. Like so. Now I want to go all the way to 4 with this. So I'm going to come back up here, and it's going to come down like this. And it's actually going to hit 4. So closed ball right about there. Little arrow here to indicate I'm going all the way up. Finally, for x is bigger than 4, I use this graph, which is my root x minus 1. So at 4, I'm actually going through this point, aren't I? If you take root x minus 1 and you plug in 4, you do get 1. So I'm going to go through this point. And then I'm going to be this parabola, which is on its side. So something like this. Okay, there is our function in all its beauty. Okay, we can see confirmed what we found earlier. We found a discontinuity here at x equals 1, a discontinuity here at x equals 3, and at x equals 4 it's actually continuous, despite the function changing definition there.